Recently, Ashok Elluswamy, Director of Autopilot Software at Tesla, gave a talk at CVPR 2022 where he discussed occupancy networks, how Tesla's full self-driving beta uses that, and also how it can be used in collision avoidance without even needing full self-driving beta. It's amazing stuff. Let's take a look. Hey y'all, it's Dr. Know-It-All. So just wanted to start with a picture of Ashok Elluswamy, who, as I said, is Director of Autopilot Software at Tesla. And I also want to point out that this video ties in very, very tightly with my full self-driving 10.69 release notes video. So if you haven't watched that yet, I will link that at the end of this video so you can watch it. And I'll link this one at the end of the other one so you can watch it, so you can just keep going around in a circle forever and ever. But anyway, what I'm going to do is start at the end of his talk, because I think that this is actually a really, really nice kind of summary of the talk and what he did. Mostly I'm going to show still frame images from his talk, and of course I'll leave a link to the original talk in the description. You should definitely check it out. By the way, it was done on June 20th of 2022 at CVPR 2022 in New Orleans, but only, as far as I know, released yesterday. So maybe they had like a 2-month moratorium on releasing it or something, because it's just coincidental that we went from 620 to 820 and then it was suddenly released. So that would be my guess. I'm not exactly sure. But anyway, Ashok talked about this and also actually did a tweet thread about this, so you can go check that out as well. But basically, in summary here, we've got create a multi-camera video network to produce dense occupancy, which is what we're going to talk about. Supervise this with large data sets of multi-view constraints, auto-labeling, and more. Generate an efficient collision avoidance field and don't crash ever, which is a pretty nice goal. And by the way, just to make a note of this, items 1 and 2 are kind of separate from 3 and 4. 1 and 2 are the foundational stuff, and they will be used in full self-driving beta. In fact, they already are used in full self-driving beta 10.69. But as far as I understand, the collision avoidance system is a separate entity from full self-driving beta and will just be included in all of Tesla's, releases. Even if you don't choose to purchase full self-driving, which by the way is going up to $15,000 on September 5th. So geez. But even if you don't choose to purchase that software, the collision avoidance software, as far as I understand it, will just be part of the package that you get with just the standard Tesla. So that means if you do something dumb like press the accelerator as you're trying to park and you would slam into a wall or a person or another car or something, the vehicle will stop itself. And actually, it's way, way, way more impressive than that. But we'll get to that later in this video. So just to recap things a little bit for those who might not know, every Tesla has basic autopilot included. Every Tesla has all the safety features, which is the reason why I believe that this collision avoidance system is going to be included no matter what you purchase as extra add-ons for your Tesla. Approximately 1 million Teslas have chosen to purchase the advanced navigation of highways, which is kind of full self-driving without the extra features for the beta. And then 100,000 people approximately have full self-driving beta, which allows people to drive all over the place, city streets, wherever you can drive. And again, just to recap here, we have 8 cameras on a Tesla. Each of them is 1.2 megapixels. That provides a 360-degree, all the way around you field of view. They run at 36 frames per second. The full self-driving hardware 3 has 144 tera operations of compute. In other words, tera operations per second of compute power. And the vehicles now rely solely on Tesla vision. In other words, they don't use radar, they don't use LiDAR, they don't even use the ultrasonics that are around the vehicle when you're driving at full speed. They only use that when you're parking and going at very, very low speeds. And finally, a huge difference between this and like Waymo and Cruise and other things is that they don't use HD maps. So in other words, nobody goes out there and maps the entire scene in very, very high detail and then the car just drives through that scene. They're making it up as they go along. So this is a really, really huge advance of the state of the art versus what other people do. All right, so Ashok starts off with the classical drivable space, the kind of state of the art from a few years ago, which basically breaks everything down, what he calls the UV space, but it's basically the image space. So it breaks everything down by pixels. It just looks at it as a flat screen and it says, where can I drive? Where can I not drive? So you see things like automobiles, cars, etc. And it says, can I drive here or can I not drive here? That's the classical sort of drivable space situation. That's got a bunch of problems. The number one problem is this is not 3D. This is a 2D image. And so you're having to make a whole bunch of assumptions and having to understand basically what the scene looks like in order to drive drive it as a 2D thing rather than a 3D thing. Also extremely sensitive to depth at the horizon. Horizons are really hard because if you think about it, there's very, very few pixels that are defining a very, very large amount of stuff that's going on. So you really do need to kind of understand that. And this system really doesn't do that well. It also doesn't deal well with overhanging obstacles, and it doesn't deal well with like vehicles and things like that because it doesn't know exactly how far away you are from all of this kind of stuff. So there are a lot of problems with this classical drivable space solution. So the next sort of iteration is to create a dense depth map per camera. And what that means is that you project out. So you can see in the right over here, I know I'm blocking part of this, but this would be this, maybe it's a Volt, no, it's probably a Chrysler minivan or something like that. But this is close by, and so you can see it's kind of an orange color. And then as we get to these vehicles that are further and further away, they get darker and darker until finally it just disappears. So close up, yeah, I mean, this orange car, yeah, that definitely gives you a sense that that's pretty close. But notice how rapidly the resolution of this thing disappears. And we get to these black pixels, you know, by the time we get to this sort of area of vehicles, like in this sort of area, it's just gone. There's no more detail left. There's no more detail about all of this stuff. So this is not a particularly workable situation either, because number one, it's still per camera, and so they don't line up with all the other cameras. But number two, it just doesn't give us enough resolution further away than like right in front of us. So what is the solution? It's what Ashok and his team call Occupancy Networks. And I'm going to show about a 3-minute clip from his talk right here, and we'll talk about it in just a minute. So let's take a look.
Here's an example prediction from our Occupancy Network. I'll pause for a moment here for you to look at the predictions. These occupancy networks take in all the 8 camera streams of input and produces a single volumetric occupancy around the car. So every voxel or every location around the car, the network produces whether that voxel is occupied or not. In fact, it produces a probability of that voxel or that 3D location being occupied or not. Like I mentioned, it takes in all the 8 cameras and produces a single volumetric output. So there is no stitching of independent predictions to produce this. The network does all of the internal sensor fusion to produce a single consistent output space. These networks produce both static occupancy, like walls and trees and things like those, and also dynamic occupancy of things that are from moving objects, such as vehicles for the most part, but sometimes there can also be other obstacles that are moving, such as debris on the road. Since the output space is directly in 3D, we can predict things through occlusions. So you can predict there's the presence of a curb, even though a car might occlude it instantaneously. Finally, this approach is extremely memory and compute efficient, even though on first sight, it might not appear so, because it produces dense 3D occupancy. It might appear that the volume might be too large, but in the end, it turns out to be much more memory and compute efficient because it allocates resolution where it really matters. Like I mentioned earlier, dense depth or drivable space in the image, there is very low resolution far away and very, very high resolution close by. But in the occupancy networks, you get almost uniform resolution throughout the volume that is relevant for driving. And that makes it extremely efficient. The networks that I'm showing here, for example, run within 10 milliseconds on our compute platform. This enables the network to be run at 100 Hertz, which is much faster than what the camera even produces the images at.
So obviously there's a lot in that 3-minute segment. And like I said, you should definitely watch the rest of it because he goes into that much detail on pretty much everything. But basically the upshot of this, and I've got a couple of different still frames from this, is that we've got this sort of voxel-based like occupancy network. So rather than figuring out where a car is and blocking off a rectangular area where that vehicle is, it's basically subdividing the scene into tiny little squares, little cubes, I guess. It's dividing it into voxels here, and so you can sort of see this. There's a roughness to it. So as he said, they're not trying to recreate a very dense mesh which would reproduce the car exactly. It's just an approximation with a couple of centimeters of latitude on either side. So it's not going to be perfect, but it's by far good enough for this car to know where it is. Because remember, we don't have to know down to like centimeter accuracy as exactly where this thing is not allowed to collide. We just need to know it's kind of in this area, right? So we can be a little bit away from that and have a little bit of error because the car's not going to try to scrape its side view mirror right against this vehicle over here, this truck that's here. It's just going to stay away from it. So it doesn't have to be perfect. And these little voxels that it has, these little cubes that are hanging out in the scene that it distributes all around the scene are perfect for that because it says don't hit any of the stuff that's in white over here or in blue over here, or in this image you can see, I guess these are more like static things like walls and curbs and stuff like that. But basically don't hit anything that looks like this, stay in the gray area. And so as he says, you've got volumetric occupancy. So it's no longer 2D, it's 3D, and it's taking account of all the cameras. So it's creating one 3D scene. It's kind of an evolution of the bird's eye view network that Andre Karpathy talked about last year in one of his talks, but it's actually 3D now instead of 2D. So the old bird's eye network, it would just look straight down and it would say like what's occupied and what's not occupied. Here what we've got is a buildup of a 3D scene instead of a 2D scene with occupancy, and that's much more robust to weird things that we'll talk about in just a second. Again, multi-camera and video context, so it's putting together the 8 cameras and it's doing video out of these cameras instead of still frames, and that actually matters a lot too. The occupancy network is dynamic. In other words, it can change every few milliseconds. It can actually update itself and it can change the occupancy of where everything is, so moving vehicles can be taken account of, etc. Very importantly, this makes it persistent through occlusions. It means that even if something blocks it, it kind of knows, like if this is a curb, something that it shouldn't drive over, and there's a car in front of it or something like that that you drive by, it knows that curb is still behind that thing. So it allows it to deal with occlusion much, much more elegantly than any of the other solutions have up to this point. It puts resolution where it matters. So in other words, it creates a volume of space around the vehicle, and it's asking where is everything in this volume of space, and just ignore everything else outside of that. So you can see that in this image right here, right? It's got the sort of neighborhood and it's got these little turnouts and things like that. And so it's got this volume of space that it's mapping out in pretty high detail, and then it's just throwing away everything outside of that because it doesn't need to know about that at this point. Now, a couple seconds later, as the car drives down this road, it will have to fill in the stuff in the future, but by then it can get rid of the stuff behind it. So it's actually a very elegant solution. And then we get to the really mind-blowing thing. It's efficient in memory and compute, and it runs at about 100 hertz. So remember, the cameras run at 36 hertz. So they're running about a third-ish as fast as this thing is. So this thing is running about 3 times faster than the cameras are even running, which is great because of course you need a lot of compute to do other things at the same time. But this is an incredibly compute efficient method that they're using now. And that actually gives me a lot of hope for the future of full self-driving, even using hardware 3. I've been concerned for a long time about hardware 3 not having enough compute power to make this stuff work, but if they're able to do things like this and reduce the memory and compute needs and have it run at these kinds of speeds, that opens up so much headroom for the current hardware in Tesla vehicles to be able to solve this problem at a very, very high bar. Okay, so how does this work? The first thing they do is they take like fisheye lens cameras, right? This is just a couple of examples here from the 8 cameras. But basically you can see how there's like, a lot of distortion in the lens. And so the first thing they do is just basic math. They can compensate for these lens distortions and they can make these things into the proper shapes and stuff. So that helps, number one, because it allows you to create the 8 camera layout and to match up these things because you've gotten rid of the camera distortion. The next step that they do is something, this is stuff I don't know particularly well. I don't know RegNets or BiFPN, which is bidirectional feature pyramid networks. But anyway, they use that. That's 2 types of neural network architectures that enable them to pull features out of these raw images in a very, very efficient manner. And I think this is still per camera at this point, right? So this is previous to them meshing the 8 cameras together. They're doing this at a very raw level. So they take the raw photons that come in, they normalize these things to get rid of lens aberrations and things. Then they run it through a RegNet and a BiFPN to pull out features that they're interested in. So after they do the RegNets and the BiFPN, they stick it through an image positional encoding system, more neural networks, but these are actually image transformers, and we can tell because there's QKV values here. So we've got query, key, and value elements, and we've got positional embedding that you can see down here. And interestingly enough, he says they used fixed queries, and so I'm not exactly sure about that. That's a different kind of thing, but what that might mean is that you're not actually training the queries anymore. You're only training the keys and the values, which is very different. The weights attached to these, by the way, just to be specific about that, so people don't call me out. But anyway, this is something that I don't know is normal. I think normally the queries are also, the weights associated with queries are also trainable. So this is a really fascinating little piece of information here. It sounds like they've got fixed queries where they're just saying basically occupied, not occupied, maybe to the level of curb, not curb, wall, not wall, vehicle, not vehicle, things like that. I'm not exactly sure. But anyway, they're using image-based transformers quite clearly here with positional encoding and the QKV, and they're producing occupancy features in a high dimensional space. Now, Ashok specifically talks about how they have to do this in a kind of a high dimensional space, and they have to reduce the resolution of this in order for it to compute fast enough. So what they're sacrificing is all of those little pixels and all of that stuff to put this in a higher dimensional space. They're then able to find out what's occupied in that space, and then they deconvolve that to get back to the higher resolution images that we would be used to. And that, of course, is what we're looking at right here. So we've got the high dimensional, lower resolution space. It's kind of a latent space for people who know the terminology. And then they're deconvolving that into a lower dimensional, but higher resolution occupancy map, which is the thing that we see, right? The thing with like the gray for where you're allowed to drive and the white and the blue and stuff like that for where you're not allowed to drive. And then we're on to the interesting slide. And I got this wrong in my earlier video about the 10.69 release notes. My bad. I said it should be epistemology. It's not. It's actually ontology. I checked the definition. Basically, it's the nature of being, but it also categorizes being into different things. So basically, the idea here is that what you see in the scene is more important than the understanding of that scene. So geometry is greater than ontology, or geometry is greater than semantics, or whatever you want to do. But here you have a really interesting example. This is a truck up here, a pickup truck with some sort of things that looks like a fence that it's carrying on a trailer or something like that. And the problem is that the previous neural network, like when you get to here, it's like it thinks it's a wall or something. It doesn't understand that that's a truck anymore. So basically the idea here is we don't need to know what this thing is. We don't still have to understand that it's a truck. We just have to know that it's an object that's sitting in the road and we can't drive through it. That's all that matters. And that's really what's important here. The geometry is greater than ontology is really, really important. The other piece of this puzzle is that Ashok said they started off doing this just for static objects, but then they realized this works so well for everything that now the occupancy network is something that they use for moving objects in addition to static objects. So not only can things slip through the ontology cracks, and we need to not worry about that, it can also slip through the moving, not moving cracks as well. And here are some more examples of ontology versus geometry. Here you've got ontology that would suggest that this is a person even though it's a statue, and that this is a person even though it's just a painting on a wall. And in this case, you might not recognize that there's a person in a Halloween costume over here hanging out by the side of the road, and this one is ridiculously dangerous. This is a person who, as Ashok says, looks from a distance like he might be a pile of garbage. It looks like it might just be a garbage bag, but that's actually a human being sitting in the road. You don't want to hit that person. So the deal here is we only need to care about whether there is something in the road that we need to not hit. We don't care about what it is ultimately. If we can visualize it and understand it, that's great, and that will help us make predictions in the future, because if you know it's a pedestrian and it looks like they're about to walk, then you can take steps to avoid that because you know there's a kinematic element. But if you don't know exactly what this thing is over here, if you're not sure what it is, you still need to avoid it even if you don't know what it is. And even as a human being, if you're driving by this fast enough, it might take you a while to recognize that that's a person in the scene and not some pile of garbage. And then, as I said, we get to the occupancy flow, which is the movement of occupancy over time. So, right, this is what we had before. We had occupancy, but it was instantaneous. It didn't understand how things were moving. So we add on to this multiple occupancy features that we stack up over time. Then we coordinate the frame alignment to make sure they're all aligned. We look at all of those and we use those to predict what's going to happen next. What this occupancy flow allows us to do is to understand what's moving and what's not moving in the scene. So if you're following behind a vehicle that's traveling at the same speed of you, you're seeing an obstacle in front of you. You're like, oh no, I can't run into that. But the occupancy flow will tell you, oh, this thing's going at the same speed as you, so you don't need to slow down, no big deal, because the occupancy is flowing away from you. Whereas on the other hand, if you're coming up on something like a truck that's crashed on the road or something like that, and it is staying still, the flow will say, hey, that thing's not moving in the scene. We better take steps to either avoid it or slow down really fast to not crash into it. So we get out of this network not just occupancy, but occupancy flow. And that's pretty remarkable considering that they're saying this is running at about 10 milliseconds per iteration. And I've got a few still frames that I pulled out of his video to look at this. The reddish color means that these things are traveling at the same speed as you in the same direction. The green means that they're traveling the opposite way. And then this white to purple is kind of still. So you can see here that these guys are reddish, right? So that means they're going the same direction as you. These guys are greenish, they're going opposite way. And then we've got white walls and purple. I think the purple just has to do with height, maybe, or something like that. And then there's white over here. He doesn't explain it. And then gray, of course, are things like cars and stuff that are just hanging out by the side of the road, parked cars. And here I didn't capture this the best, but up here is kind of a weird little backhoe thing. Not a standard car to be in the road, but basically the car recognizes that there's something in the road, even though it doesn't know what it is, and it takes steps to avoid that. So that's really important, right? Because you're not going to always see something that you recognize. You just have to recognize that something is there. And then we get this really cool image that may not look like a lot, but if you look up here, you can see that this truck has a thing that's sticking out at the end of it. It's like a jack. I assume that there's a cherry picker up above it, and so it's just something to make sure that it's a very, very stable base. But you can see how this system can now visualize that. So as opposed to just visualizing a truck as a rectangular box and not seeing that and potentially hitting it, which would be really bad, here you've got, I don't understand what it is, but it's in the road and I'm going to avoid it, which is absolutely critical to making sure that full self-driving works as well as possible under as many circumstances as possible. And of course, this also helps with occlusion. You can see that cars that are partially occluded by signs and trees and things, again, remember the red is going the same direction as the car is heading, that it will be able to model these things even when it can't see them for part of the time. And that is actually a really huge benefit to this as well. And that has to do with the fact that we've got occupancy flow, because we're like, okay, this thing is moving and that's where the occupancy is going. So even though I can't see it for a second, I'm going to predict that it's going to appear on the other side of this obstacle in just a second because it was flowing along. So because we're not looking at occupancy instantaneously, we're looking at it as a flow over time. It's able to deal with occlusions and handle that stuff really, really well. And then we get to some really, really interesting stuff about NeRFs, which are neural radiance fields. Those are a projection of 2D images into 3D space. It's very, very cool. I'll show you a still frame of this from here. Well, a couple of still frames, but this is actually a 3D reconstruction of a scene rather than the actual scene. So you can see it's kind of blurry in places, but it's super, super cool how it's able to do that by basically projecting rays into a scene and producing this scene. So it's very, very cool. And this NeRF actually gives you two things. Number one, it can be used for training. And it's important to note that this is not real time as far as Ashok was talking about. What you do is you create these images in training sets so that you have some sort of a ground truth to react against your occupancy networks. So you can take the occupancy network, you can then take the radiance field and you can look at it and you can match them up and say, where's the loss? Where are things not matching up? And you can use that to help train the neural networks to get better and better. But then even cooler, Ashok says that there's like a mini version of this that's actually inside the car running all the time, which is also looking at loss. So it's not doing a full resolution radiance field, but it's doing kind of a mini one and it's constantly checking. So it's kind of like a sanity check, I guess. So you're doing an occupancy network and then sanity checking it against this radiance field. Now, Ashok does discuss the fact that there are issues with radiance fields because you can have things like dirt and smudges. You can have stuff like the sun shining in it. So that can mess things up. But I guess what they're doing is they're actually taking fleet averages. So if multiple cars over multiple times of day drive through the same intersection, they can create that radiance field not just from one car's data, but from all of these cars. They can merge it together and create a very high quality radiance field, which is pretty darn remarkable. And then what they can do is they can use that to create descriptors, which are more robust than the raw RGB pixels. So here you can see it's kind of a semantic segmentation of the scene, but basically, it's saying like, here is a person, here is a person, here is a palm tree, I think, or some kind of tree, here is a tree, here is a building, here is a building. So it's segmenting that out. Here is a car, here's a car. So what it's doing is it's segmenting this out, and that is more robust because it's not raw pixels that it's producing, but it's actually something that has some level of meaning to it. And so these radiance fields can be very, very robust to changing lighting conditions, to whether the camera has a perfect view or not, et cetera, et cetera. And so finally, we get kind of an overall view of how all of this stuff works together, right? We have occupancy flow, all the stuff that goes into it. We get occupancy flow from here, and then we match it up, and sorry, I'm right in front of that, but this is the neural radiance field. The NeRF gives it a bit of feedback and tells it whether it's doing it right. So not only are we able to train at non-real-time speeds, but even during real-time activity, by using a smaller version of this NeRF, we're able to get real-time feedback about the occupancy flow. So there's kind of a double checking thing just to make sure that no errors are accumulating. So that is really, really awesome stuff. All right, and then we turn to the second half of his talk, which is collision avoidance. This is not really part of full self-driving beta. As I said at the beginning, this is something that's its own independent thing to make sure that the car doesn't crash into stuff. And he runs through a simulation where they simulate somebody driving by just stomping on the accelerator pedal, and the car, like you can see, it kind of swerves back and forth, but it stays in the middle of the road, doesn't crash into anything, and slows down when it needs to. So that's the kind of thing we're talking about. This is going to be built into every single Tesla, no matter whether you get full self-driving or not. And that is pretty cool. I'm going to go through this a little more quickly because there's not so much technical detail here, so it's easier to understand. But basically 40 accelerator misapplications every single day from their fleet, which is pretty remarkable. So this also gives them a lot of data. But basically this is the thing. This person is standing in front of the car. The person meant to brake or do something, but they stepped on the accelerator. And if the car had not stopped, that car would have collided with that person and squashed them between the parked car and this other vehicle, which could have injured them very, very badly. So this is a situation where, that's a really important thing for safety. And by the way, Teslas already do this, just as a note. This is not something in the future. This is something they already do. But as Ashok said, you can avoid many collisions, but many more remain to be prevented. And that's what this new network can do. So Ashok spends a little bit of time talking about the fact that it's not just avoiding accidents. You can't just slam the brakes on all over the place and turn really, really radically. It's got to be safe, so avoid accidents, but it's also got to be comfortable. So it has to think ahead, and it has to slow down, in a comfortable manner, not something that's completely jerky and terrifying to people, or could cause the person behind you to ram into you because it slows down so fast. And of course, it's got to be reasonably fast. It's got to understand the scene quickly enough to be able to react to it quickly. So how is this done? It's actually very clever. They take the occupancy network, they throw it through an obstacle encoder neural network, and then they throw it through a little itty bitty, he calls it a small MLP or multi-layer perceptron, and that goes to a collision avoidance probability situation. So basically it maps out for the scene collision probabilities, and it says, am I going to collide with something? I better look around and I better make sure I'm not. And if it looks like it's going to, then it can act on it through policies. So here you can see sort of a top-down 2D view, right? This is stuff that you're not supposed to drive into. That's something that you could collide with. The gray is stuff that you can drive on, and the white is like lane markings, etc. And it makes a little more sense when you look at it in color. So now what you've got is this car driving at this speed, if it's going this direction instantaneously at any point. So if you move this car from here to here, it's probably going to collide. If you move this car from here to here, it's definitely going to collide. So this is sort of instantaneously in this orientation going this speed. Will it be colliding with something right now? But we can get a lot more clever than this. We can actually look at a 2-second horizon. We can say, is this not just colliding right now, but will it collide with something in 2 seconds? So notice this car is driving pretty fast at this almost right angle here. So not so good. And if we moved it from here to here, it's also going to collide with things, etc. But as the car rotates to more along the alignment of the road, you can see that there's a little green path that starts to appear. So the car can figure out where it is, what direction it's heading, how fast it's heading, and whether, if it keeps going that way, it's going to be able to be safe or whether it's going to collide with something. And of course, they can vary the velocity and the heading at the same time. I guess it would be the speed and the heading, since the velocity is both of those together. And so you can see this is really cool. The car starts back here and it starts to make a turn because it sees it's going to collide. And then it starts going over in this direction, and you can sort of see a collision, non-collision sort of representation in 2D over here. And as it figures it out, it kind of straightens itself out, drives down the middle, and gets up here, and it's all green. So it's actually done a great job of avoiding the collision. So this is not just an instantaneous, like I stepped on the gas pedal when I meant to step on the brakes and it will do something right in that second. You can see that this actually would, if you just stepped on the accelerator and close your eyes or something, this thing would manage to avoid stuff and continue driving. So that is a pretty remarkable, hugely important safety feature that they're going to be building in as soon as the next software revision coming out. So this is incredibly important stuff. And then, as I said, Ashok shows some simulations. So these are not real. Remember, they've got really, really high resolution simulations that they can run, but they basically simulated somebody just stomping on the accelerator pedal, and they watched in the simulation the car avoid running into things. So again, watch the video. He actually shows this. It's really cool watching the thing kind of go like, through the streets and manage to avoid hitting anything. And that brings us back to where we started. So we create a multi-camera video network to produce dense occupancy maps that also flow over time. We supervise this with large data sets of multi-view constraints, auto labeling, NeRFs, all of that kind of stuff. And then we move on to the collision avoidance network, which is that we can generate an efficient collision avoidance field, which doesn't take a long time to run. It runs very, very rapidly, low memory, low compute costs, but it's very, very high quality. And then you don't crash ever, which is incredible. So as Ashok's talk should show you, we have got an amazing plethora of new things that are built into Tesla's full self-driving. They're rolling this stuff out all the time. And it's not only incredibly important for autonomous driving, it's important for just basic safety. No other brands of vehicles are going to have these safety features built in. This is just remarkable stuff. And so even if you don't care about autonomous driving and full self-driving, you should really care about the fact that Tesla will keep you from colliding with things, even if you're stupid enough to make a mistake. And that, my friends, is pretty amazing stuff. All right, I hope you enjoyed this particularly geeky episode and found it fun and interesting and thought-provoking. If you did, please do like it so other people can find it, because that's how YouTube's neural networks work. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon. Thank you all so much for your support. I really do appreciate it. We've talked a lot about this stuff. A lot of people are tracking 10.69 releases and all of that kind of thing. So anyway, it's very, very cool to be part of the community, and I really do appreciate it. And of course, if you want to join the team, just check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, Success is a Possible Outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on. So check it out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.